Good morning, everyone. My name is Aditya from BSC Chemistry Honors final year. Today, I am here to give a video on the visually impaired for the students having the topic carbohydrates. Let's start with the introduction. One of the important classes of biomolecules is the carbohydrates. These include the compounds like sugar, starch, glycogen, cellulose, dextrins, and gums. Although they are widely distributed both in the animal and plant kingdom yet, since they are obtained mainly from the plants. They are found in the plants by a process known as photosynthesis and make up to about 70% of the solid plant material. Having let's take a reaction to understand, taking the X mole of carbon dioxide and Y moles of water in the presence of sunlight and chlorophyll will give the carbohydrates having the formula CxH2O of Y plus the X moles of oxygen. Carbohydrates play a vital role in our daily life. They provide us the three basic necessities of life, that is, food in the form of starch, clothing, that is, cotton, linen, rayon, are essentially cellulose, and shelter, that is, wood in making houses and furniture, is almost the cellulose. Classical definition: the name carbohydrate, meaning the hydrate of carbon, was originally given to a classes of compound containing only carbon, hydrogen, and oxygen. The hydrogen and the oxygen being the present in the same ratio as in water. These compounds could therefore be represented by the general formula CxH2OY, the limitation of the old definition. The old definition could not survive long due to the following reasons. A number of compounds such as ramenose and deoxyribose are known, which are carbohydrates by their chemical behavior but can't be represented as the hydrates of carbon. Second point is there are the substances like the formaldehyde and the acetic acid which do not behave like carbohydrate and but can be represented by the general formula. Carbon is not known to be the hydrates. Modern definition: carbohydrates are defined as the polyhydroxyaldehyde or polyhydroxyketones or substances which give these on hydrolysis and contain at least one chiral carbon atom. It may be noted that here aldehydic and ketonic groups in carbohydrates are not present as such but usually exist in the combination with one of the hydroxyl group of the molecule in the form of hemiacetals and hemiketals respectively. Classification of the carbohydrates. Carbohydrates are known as saccharides and they are classified into the three classes depending on the behavior towards hydrolysis. First class is the monosaccharides. These are the simplest carbohydrates which cannot be hydrolyzed to a smaller molecules. Their general formula is CH2ON, where N is ranging from 3 to 8. Oligosaccharide, Greek in oligo means a few. These are the carbohydrates which on hydrolysis give the 2 to 10 molecules of the monosaccharides. Depending upon the number of monosaccharide molecules actually obtained upon hydrolysis, they are further classified as di, tri, tetra saccharides, etc. For example, the disaccharide which give only 2 molecules of the monosaccharide. Third class is the polysaccharides. The carbohydrates which upon the hydrolysis give a large number of monosaccharide molecules are called as polysaccharide. The most commonly occurring polysaccharide are starch, cellulose and glycogen. Their general formula is C6H10O5N where N ranges from 10 to 3000. Sugars and non-sugars. Carbohydrates are further classified as sugars and non-sugars. All the mono and oligosaccharides are crystalline solids and soluble in water and sweeter in taste. These are collectively called as sugars. The polysaccharides, on the other hand, are amorphous solids and insoluble in water and tasteless and thus called non-sugars. Reducing and non-reducing sugars or carbohydrates. Carbohydrates are also classified as the reducing and non-reducing sugars. All those carbohydrates which contain aldehydic or ketonic group in the hemiacetal or hemiketal form and reduce the tolling reagent or filling solution are called as reducing carbohydrates, while other which do not reduce these reagents are called non-reducing carbohydrates. All monosaccharides, whether aldoses or ketoses, are the reducing sugars. Disaccharides such as sucrose, in which two monosaccharides units are linked through their reducing center, that is aldehydic or ketonic groups, are non-reducing, while others in which these groups are hemiacetal or hemiketal forms are reducing sugars. Hence, all polysaccharides are the non-reducing carbohydrates. Now see the classification of the monosaccharide. As stated above, monosaccharides are the simplest carbohydrates which cannot be hydrolyzed to smaller molecules. These contains up to 3 to 7 carbon atoms. There are about 20 monosaccharides which occur in nature. For example, first of all, they have two types. First of all, it is aldoses. Monosaccharides that contain an aldehyde group are called as aldoses. Since the aldehyde group is monovalent, therefore it only present in the end of carbon atom, that is at C1. Ketosis. Monosaccharides containing a keto group is called as ketosis. Since the keto group is divalent, it can be present anywhere along the carbon chain. However, in all the naturally occurring ketoses, keto group is always present at the next to terminal carbon, that is at C2 position. Aldoses and ketosis are further classified as triosis, tetrosis, pentosis, hexosis, heptosis according to as they contain 3, 4, 5, 6 or 7 carbon atoms respectively. The classification of the monosaccharides is summarized in table 1.1. Now see what is dextrose or the grape sugar, having the molecular formula C6H12O6. It is also determined as glucose. Glucose is the widely distributed monosaccharide. It occurs free in the large quantity in ripe sugars, that is why it is called grape sugar. It also occurs in honey and most of the sweet fruits such as mangoes, apples, peaches, pears, etc. It is also present in human blood by 0.1%. In the combined state, it occurs in glycosides, disaccharides, and polysaccharides. Preparation of the glucose. In laboratory, it is prepared by the hydrolysis of the sucrose, by giving the 2 units of glucose and fructose respectively. 5 or the manufacture sucrose is hydrolyzed by heating with dilute HCl or H2SO4 in 90% alcohol when a mixture of glucose and fructose is obtained. Glucose, being almost insoluble in alcohol, separates out on coiling while the fructose remains in a solution. On a commercial scale, glucose is prepared by the hydrolysis of starch with the hot dilute mineral acid. The chief source of starch are rice, maize, and potatoes. Physical properties of glucose. Glucose is a crystalline white solid with melting point 419 Kelvin, and it is highly soluble in water but sparingly soluble in alcohol and insoluble in ether. It is optically active and is dextrorotatory compound, hence having the name dextrose. It is about third-fourth as sweet as the sucrose, that is the table sugar. Chemical properties of glucose. The D plus glucose is typically a monosaccharide and give the reaction of both the aldehydic and alcoholic groups. In order to discuss these reactions, glucose may be simply represented as the open chain pentahydroxyaldehyde shown below. Reactions with the phenylhydrazine. Glucose reacts with 1 mole of the phenylhydrazine to form the glucose phenylhydrazine. Osazone preparation. However, if excess of phenylhydrazine is used, the reaction proceeds further, yield a crystalline compound known as osazone, which contains two phenylhydrazine residues per molecule of glucose, while the third molecule of the reagent is converted into the aniline and ammonia. It may be pointed out here that osazone formation is not only a characteristic reaction of the reducing carbohydrates, but it is also given by all the alpha hydroxy aldehydes and alpha hydroxy ketones in general, example benzoin. Further reducing the osazone formation, the stereochemistry about C2 carbon atom of aldose is destroyed without affecting the configuration of the rest of the molecule. Fischer's mechanisms. Emil Fischer, who first prepared the osazone, explained the mechanisms of its formation below. The first molecule reacts in a usual manner expected of an aldehyde. The second mole oxidizes the secondary alcoholic groups to the ketonic groups, and the third mole react with the keto group and thus generate to form the osazones shown below. Limitation of the Fischer mechanism. The above mechanism, however, suffers from the following defects. It does not explain why the phenylhydrazine, which is a strong reagent, act as an oxidizing agent in the second step of the above mechanism. It does not explain why only the first two carbon atoms are involved in osazone formation. That is, why do the remaining hydroxyl groups not get oxidized and react further with phenylhydrazine. Now see what is the modern mechanism. To overcome these objections, Wiegand proposed an alternative mechanism involving the amidori rearrangement. The phenylhydrazine thus formed undergoes tautomerism to form a hydrogen bonding six-membered intermediate. This intermediate subsequently loses a molecule of aniline to form a aminoketone 1, and the aminoketone then reacts with the two molecules of the phenylhydrazine, one at the carbonyl group and other at the C double bond NH to give the final osazone. This mechanism is supported by the observation that phenylhydrazine is prepared from the 15N labeled phenylhydrazine and is treated as the ordinary phenylhydrazine. Unlabeled osazone is formed with the elimination of the labeled ammonia. The mechanisms also not explain why the reaction stops after the addition of the two phenylhydrazine residues. This has, however, been explained on the basis of osazone is stabilized by the chelation as shown below in the and the further reaction will stops. Now see the open chain structure of the glucose. The structure of glucose is discussed under the following subheads. First is the open chain structure. Molecular formula of the glucose as determined from the analytical data and molecular weight is C6H12O6 and the presence of aldehydic group. The glucose reacts with the HCN to form a cyanohydrin with hydroxamyl amine to form a oxime with equimolar contents of the phenylhydrazine to form a phenylhydrazone. All these reactions suggest that the presence of a carbonyl group in the glucose. C6H12O6 glucose reaction forming the cyanohydrin oxime and phenylhydrazine. Presence of 5-hydroxyl group. When treated with the acetyl chloride or hydride, it forms pentaacetate, which furthermore shows that the presence of 5-hydroxyl group. Presence of one primary alcoholic group is shown by the oxidation with nitric acid, which gives glucaric acid, that is a dicarboxylic acid containing the same number of carbon as glucose. One of the carboxyl group in the glucanic acid must have been produced by the oxidation of the aldehyde group, and other must have been obtained by the oxidation of primary alcoholic group. Thus, one of the hydroxylic group are present in glucose must be a primary alcoholic group. Presence of the straight chain of carbon atom. Glucose on reduction with the hydrogen iodide and the red potassium at 373 Kelvin gives a mixture of N-hexane and 2-iodohexane. This indicates that 6 carbon atoms in glucose are arranged in a straight chain. From the above discussion, it is follows that the glucose contains one aldehyde group, 5 hydroxyl group, out of which one is primary, a straight chain of 6 carbon atom. Further, since the aldehyde group is monovalent, it must be present at the end of the chain. Keeping in view these facts and the tetravalency of carbon atoms, the following open chain structure was proposed for the glucose. The configuration of the glucose. The open chain structure of glucose contains the 4 chiral atoms marked by the archatrix. Therefore, it should exist in the 16 optically active stereoisomeric forms. All these 16 stereoisomers are known and exist as a pair of enantiomers, 8 belonging to D series and 8 to L series. Therefore, in fact, corresponding to D and L form of allose, altrose, glucose, mannose, glucose, idose, galactose, and talose. Out of these stereomers, one is D plus glucose and its other is enantiomer, L minus glucose. Configuration is given on the page. The rest 14 being diastereomers of D plus glucose. However, there would be no mesoforms since the ends of the molecule are dissimilar. The absolute configuration of the D plus glucose was established by the Emil Fischer in 1891, who was awarded the Nobel Prize in 1902 for this work. The details of his procedure is, however, discussed in the section 2.0 under the experimental proof of the absolute configuration of aldoses. D plus fructose or fruit sugar having the formula C6H12O6. It is the most important of all the ketones. It occurs free along with the glucose in the form of invert sugar in honey and in sweet fruits. In the combined form, it is present in disaccharides and polysaccharides. Preparation of the fructose. D-fructose in the laboratory is prepared by the hydrolysis of the cane sugar or sucrose with the dilute sulfuric acid. On a commercial scale, it is prepared by the hydrolysis of inulin, a polysaccharide present in the HeLa tubers, and gerosylin architects with the sulfuric acid. The excess acid is neutralized with the barium hydroxide when barium sulfate get precipitated and is filtered off. The filtrate is concentrated by the evaporation under the reduced pressure to get crystals of fructose. Physical properties of glucose. Fructose is a colorless crystalline solid with melting point 375 Kelvin. It is sweetest of all sugars and it is more soluble than alcohol than glucose. It is optically active and levorotatory and hence levolose. Chemical properties of glucose. It contains one ketonic group, two primary and three secondary alcoholic groups. As such, it gives reactions of both alcohols and ketones. Some of its reactions are: with hydrogen cyanide, it forms the fructose cyanohydrin. With hydroxylamine, it forms the fructose oxime. With the action with phenylhydrazine, it forms the fructose phenylhydrazone, and with ozone formation, it forms the fructosazone, as does the glucose. Similarly, the mechanisms are also same. Fifth reaction is oxidation. It is not oxidized by the mild oxidizing agent like bromine water. Strong reducing oxidizing agents like concentrated nitric acid oxidize fructose to give a mixture of three acids, each containing lesser number of carbon atoms, which are trihydroxygluconic acid, glycolic acid, tartaric acid. Reducing nature. Unlike simple ketones, reduces the following solution and tolerance reagent. This is due to the reason that under alkaline medium of these reagent, First, glucose undergo Lowry-de-Bruyn when enkystin rearrangement to form a equilibrium mixture of glucose, fructose, and mannose. Glucose and mannose thus produced bring about the reduction of these reagents. Reactions of hydroxyl group. Acetylation. Fructose with the acetyl will give the fructose pentaacetate. Action with methyl formation, methyl alcohol formation of the methyl fructosides. Fructose with the acetone will give the alpha and beta methyl fructosides. Open chain structure of fructose. Molecular formula. Molecular formula of glucose as determined from elemental analysis is 6,6H12O6, presence of the ketonic group. Fructose react with the hydrogen cyanide to form a cyanohydrin and hydroxylamine to form an oxime with the equivalent amounts of the phenylhydrazines to form a phenylhydrazone. All these reactions suggest that fructose contains a carbonyl group. Now see the interconversions of glucose and fructose. Conversion of a aldose into the isomeric ketose. Conversion of the glucose into fructose. An aldose such as glucose can be converted into the isomeric ketose such as fructose via the oxazone illustrated below. First of all, glucose is reacted with the phenylhydrazine. Then it reacts upon hydrolysis will give the glucosazone, which on reduction with the zinc in the presence of the acetic acid gives the fructose. Now see the chain lengthening and chain shortening of the aldoses. An aldose can be converted into the next higher aldose containing one or more carbon atom by the Killiani-Fischer synthesis discussed below. First of all, we have taken a arabinose on which cyanohydrin will give the glucosanitrile, on which reaction with hydrolysis will give the gluconic acid, and the loss of water molecule will occur through it by heating it, and we get the gamma lactones. Now on reduction by the sodium in the presence of mercury of water, it will give the glucose. The Killiani-Fischer synthesis is illustrated by converting arabinose into the glucose and mannose, both aldohexoses. Shortening of the carbon chain, which is degradation. There are two types of degradation. First one is the Ruff's degradation. In this method, the aldose is first oxidized with bromine water to the corresponding aldonic acid, which is then converted into calcium salt by the treatment with calcium carbonate. The calcium salt is then treated with the Fenton's reagent in the presence of the Fe3 positive ions when the oxidative cleavage occurs between C1 and C2 bond to give the lower aldoses. Second degradation is the Wolff's degradation. Wolff's degradation is essentially the reverse of the Killiani-Fischer synthesis. In this method, the aldose is first converted to its oxime by treatment with the NH2OH, which is then heated with the acetic anhydride in the presence of the sodium acetate. During this treatment, all the hydroxyl groups are acetylated and at the same time get dehydrated to a cyano group. The resulting acetylated cyanohydrin on treatment with ammoniacal silver nitrate or with the sodium ethoxide, that is the Xamphen modification, undergoes the simultaneous deacetylation and elimination of the hydrogen cyanide to give the lower aldoses as shown below. Now see the limitations of the open chain structure of glucose. Although the open chain structure of glucose explains most of the reaction, yet it's failed to explain the following facts. D-glucose do not get the certain characteristic reactions of the aldehydes. For example, glucose doesn't form the sodium hydrosulfide addition products aldehyde ammonia and does not respond to Skiff's reagent test. Glucose reacts with the NH2OH to form an enzyme, but glucose pentaacetate does not. D plus glucose exists in two stereomeric forms, that is D-glucose and beta-D-glucose. Alpha D glucose is obtained by ordinary temperature, is allowed to crystalline form or aqueous alcohol at room temperature. It has a melting point of 419 Kelvin and has a specific rotation of about 112 degree in a freshly prepared aqueous solution. However, when glucose is crystallized from water above 371 Kelvin, beta D plus glucose is obtained. It has a melting point of 423 Kelvin and has a specific rotation of plus 19 degree in freshly prepared aqueous solution. D plus glucose forms two isomeric methyl glucosides. Aldehydes normally reacts with 2 mole of methanol per mole of the aldehyde to form an acetal, but D plus glucose when heated with the methanol in the presence of dry HCl gas reacts with only 1 mole of methanol per mole of glucose and forms a mixture of two methyl D glucosides. That is the methyl alpha D glucosides and beta methyl D glucosides, having the melting point 380 Kelvin and specific rotation is minus 33 degrees Celsius. Ring structure of glucose. In order to explain the above facts, Tolan suggested that glucose doesn't have a free halide group but it has a cyclic hemiketal structure. He argued that the OH and CHO groups are a part of same molecule. Therefore, any of the OH groups may involved in intramolecular hemiacetal formation. Since gamma hydroxy acid readily undergo electronization, he suggested that the glucose has a 5-membered ring, that is C4OH, involved in hemiacetal formation. This structure is called as gamma glucose. Evidence in favor of the ring structure. The phenomena of metarotation executed by the glucose anomers can be explained in terms of its cyclic structure. Each of these anomers has a typically hemiacetal and can be hydrolyzed to the aqueous solution to give the open chain form of glucose. Therefore, in the aqueous solution, either anomer is converted through the open chain form into an equilibrium mixture consisting of both the anomer with a very small amount of open chain form. The equilibrium mixture has a specific rotation of about 52.7 degree. Thus, the phenomena of the meta-rotation is due to the facile opening and closing of the hemiacetal ring. The typical aldehydic reactions of the glucose, such as cyanohydrin, oxime, and oxazole formation, reduction of the filling reagent, etc., can be explained in terms of its small amount of the open chain form present in equilibrium mixture of the two anomers. Hence, as the open chain is consumed during the formation of this derivative, the equilibrium is disturbed. Most of the open chain results to push the reaction in forward direction. Ultimately, the whole glucose reacts via its open structure to form of these derivatives. In contrast, the aldehydic reactions of glucose with Skiff reagent, that is sodium bisulfate and ammonia, are reversible and the concentration of the open chain form is the equilibrium mixture is too low. As a result, these weak reagents cannot disturb the equilibrium to form the open chain form, and hence these reagents not react with the D plus glucose. The formation of anomeric methyl glycosides can be explained in terms of its cyclic structure. The equilibrium mixture of alpha and beta glucose react separately with the methanol in the presence of dry HCl gas to form the corresponding methyl D glucosides. Like methyl glucosides, glucopentaacetates also exist in the two anomeric forms as shown below, that is alpha D-glucopyranose pentaacetate and beta D-glucopyranose pentaacetate. These pentaacetate do not have a free OH and group at C1 position and hence do not hydrolyze in the aqueous solution to produce the open chain aldehydic form and do not react with the NH2OH to form a glucose oxime. A limitation of the open chain structure of fructose. The open chain of fructose formol has accounts for its most properties but fails to explain the following facts. Fructose does not react with sodium bisulfite, and even though it contains a ketonic group. It exists in two stereomeric forms, that is D-fructose and beta-D-glucose with show meta rotation. Pyranose structure of D-fructose. To explain and certain effects, it was suggested that fructose exists in a cyclic hemiketal structure. It was assigned a six-membered hemiketal or pyranose structure, which is formed by the combination of the ketonic group at C2 position, hydroxyl group at C6 to give rise to alpha and beta defructose as shown below. Furanose structure of fructose. Although in the free state, fructose has a six-membered cyclic or the pyranose structure, but in the combined state, as in fructosides, disaccharides like sucrose, etc., fructose always has the cyclic structure or the furanose structure. Now let's see what are the difference between starch and glucose. Starch, it is a chief food reserve for the material or storage of polysaccharides of plant and is formed mainly in seeds, roots, tubers, etc. Wheat, maize, rice, potatoes, barley, bananas, and sorghum are the main source of starch. Starch occurs in the form of granules which vary in shape and size depending upon the plant source. Cellulose is widely distributed in plants. In fact, more than 50% of the living matter is cellulose. It is a chief structural material and cell walls of all the plants. It is also the chief component of the cotton, wood, jute, etc. Wood contains about 45 to 50% cellulose, rest being lignin and resins. Cotton contains about 90 to 95% of cellulose, rest being fast and waxes. Starch is made of two components, amylose that is 20% and amylopectin that is 80%, whereas cellulose is a single compound. Both amylose and amylopectin are conjugation polymers of the D-alpha glucose. Cellulose is a combination of beta-D plus glucose, whereas the amylose has helical structure in which D-glucose units are joined by the alpha-1, for glycosided linkage. Amylopectin has a branch structure. It consists of several hundred short chains, each consisting of about 20 to 25 short chains and joined together through alpha glucosidic linkages involving C1 of the one glucose with the C1 of the other. Cellulose has a linear chain structure of 3000 glucose units which are joined together to form the beta glucosides linkage involving C1 of the glucose with C1 of the other. Amylose give a blue color with the iodine solution, whereas cellulose do not give a blue color with the iodine solutions. Starch is the main source of energy for human beings and cellulose do not adjusted by the human beings. Uses of cellulose. Cellulose is mainly used as a raw material for textile industries. The chemical treatment of cellulose with the different types of reagents yields several different products which are useful as the commercial products as below. Let's take an example, that is rayon. It is a chemical name given to all fibers made by the chemical treatment of the cellulose. These are the acetate rayons and viscose rayons. Thank you.